Hello? Can you hear?
Talk, talk, talk. Sound, sound, sound on the stream. Everybody have sound coming
Check, check.
on the stream.
Okay, it's not. No, this is not green yet. Like this ring is not green.
Do we have sound? 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 Sound?
I bet.
Good morning, everybody. Welcome to Chem 1A, day after the holiday. Hope you guys had all a good long break. It kind of sucks that there's a break and you have an exam right when you get back, so you kind of feel like you got to study. And exams, are stressful. I remember. I was a student. I was a student once too, as you may know. Exams always upset me. Sometimes, getting physically nauseous. So I'll try to go through the topics of the exam here right now, so and I'll try to do it, without I don't know, getting flashbacks already. If I can do it. Okay, deep breaths. All right, so the exam topics will be, stoichiometry, the structure of basic atoms and moles. Okay, I'm good. We're gonna go through thermodynamics, so energy conservation, and free energy, equilibrium, the nature of spontaneous processes. Oh, whew. You're responsible for all of that. I'm glad that I am not. I am. I spent my weekend. As you know, it's not trivial to put the exam together, especially since we have to upload it onto the website, and we have to be done far enough advance for your undergraduate instructors to go through and look at it so they can suggest edits and find errors. So hopefully it'll be ready for you to go. The exam will start 6 p.m. tonight or 6 a.m. Tomorrow morning, depending on where you've signed up with Sydney for your time zone choice. And the exam will run for 100 minutes after the start time. So if you start a little late, you just have 100 minutes from 6 p.m. or 6 a.m. to continue. It's all 100%. Well, it's not 100% multiple choice. At the end, there's a short answer that will be graded separately from. So you'll get a score, and then that short answer will be added sometime later in the semester. So that's how it is. That's the format. I think it's going to be about, what is it now? 33 questions, 34, somewhere on the order between 35 and 40 multiple choice questions. So let's review. We're going to do a bunch of chem quizzes that focus very well on exact topics you'll see on the exam. So we'll start with a review of where we're trying to go, and where we're trying to go is to understand this entire picture. We understand now how atoms and molecules combine, and we can use relative masses to determine that we have the correct number of particles on products and reactants. We can predict if particles will be used up, if they'll be left over, by using simply relative masses, or the mole concept. We have moles of each of these, and a mole is just a set number of particles. So you can use those concepts either way. And we know how to balance chemical reactions. That's the whole idea of stoichiometry. So that is a portion of the exam. The structure of the atom. I assume you kind of know the structure of the atom. We breezed right by that. There's not a lot of focus on the structure of the atom in the exam. I think you know it. You have to use it, and we'll have to use it much, much more as we go forward. So it's not important that we focus this time. This was the main focus of the first 2 weeks, which is getting essentially from reactants to products, and talking about all the energetics involved with that, and some of the new, more mysterious stuff, the entropic effects, the statistical effects. And remember to separate the statistical effects, the entropic effects, from the energetic effects. So those are two different things. You have your potential energy, you have your kinetic energy, you have bonds breaking, bonds formed, but the statistical arrangement is in general independent of those, except for conditions where you're going to use the heat flow to calculate how microstates are changing. So we have a thermodynamic definition of entropy and a statistical definition of entropy. And the thermodynamic definition says, if you do something at constant temperature, you can take the heat evolved or absorbed by the system, say the heat absorbed by the system, and divide that by the temperature. And as long as you do that carefully, and then you won't have to worry about the carefully part, just do it. Heat over a constant temperature, that's the thermodynamic interpretation of entropy, but it jives directly with our idea of the statistical nature, because absorbing heat increases the relative motions of the particles, or they can occupy more space, and that allows them to occupy more microstates, but more microstates at the same energy. So all the microstates have to be accessible at the same energy. That's what gets you this randomness. So, and we talked about for a gas, importantly, and all the gases on the exam, treat them completely ideally if it's in the gas phase. That means the particles don't interact. And you can ignore potential energy in the gas phase. So there's no attractions between the molecules or the particles. So just a completely ideal gas. And we said for completely ideal gases, the energy was obvious. It's always directly related to the temperature. It's proportional to the temperature. So if the temperature changes in a system of pure gas, that is a kinetic effect, and it's reflected directly in the temperature. So we have those ideas in mind. We talked about how to deal with heat effects in condensed phases. We talked about heat capacities. So the gases can have heat capacities, of course, but in the condensed phases, metals have heat capacities, water have heat capacities that determine how much heat you absorb for a unit temperature change. How much do you have to absorb to get a change in temperature? So all that involves our molecules, our mixtures, our reactions, and these how they get from products to reactants. We found that one of the best energy parameters to plot was free energy, because free energy, reactants and products, if you have that negative, that reduction in free energy, delta G for reaction is negative, that tells you this is a predictive plot. It's going to low energy. So this is the analogy to the gravity case. Downhill in free energy is the real downhill of chemical reactions. It's not entropy. Entropy can increase. Enthalpy can increase. But the real downhill is free energy. And that's why we stopped there. Or that's why we got there. Free energy is related to the entropy change of the universe. So very importantly, for any process, the entropy change of the universe increases, except in very specific cases where there's an equilibrium, or what we call a reversible process. All other processes are irreversible or spontaneous or favored by the universe, and those go with an entropy increase in the universe. Now remember, that doesn't have to be just the system. It's the system plus the surroundings. All the entropy change that's positive could be happening in the surroundings. The system can get to lower numbers of microstates as long as there's a compensatory greater entropic effect in the surroundings. And that leads to this rather depressing law that energy, free energy, enthalpy, those are conserved. If you go around a full pathway, initial state equals final state, delta E, delta H equals 0, because your initial state and your final state are the same. If you go around a complete circle for the entropy of the universe, that's always positive. You gain, entropy increases even if you go around the complete circle. If you're super careful, you can keep the entropy of the system to come right back to where it was. But even if you get the entropy of the system to come right back where it was, that creates entropy in the universe. That's not conserved. So that told us a lot about how these things work. We talked about adding a catalyst, and we're going to talk much more about that as we go through tomorrow and the kinetic portion of this picture. But let's do a series of chem quizzes. So this is what we talked about for our stoichiometry, our conservation of mass. If you start out with 36 grams on one side, you have to end up with 36 grams of material on the other side. The number of molecules does not need to be conserved. You can start out with one molecule on the other side and two on the other. That's absolutely fine. The number of moles does not need to be conserved. The number of particles does. Total particles, they can be rearranged differently, but total particles jives completely with total mass. Each particle has a mass. So mass conserved, energy conserved, entropy not conserved. So let's do a chem quiz that talks about these mass ratios. A compound contains hydrogen, oxygen, carbon, and sulfur, and it contains it in these mass ratios. So 1 hydrogen to 2 relative masses oxygen, 3 relative mass of carbon, and 4 relative masses of sulfur. So there's 4 times as much sulfur by mass as there is hydrogen by mass. The question is, what is the empirical formula? So if you know how they're combining mass per mass, can you convert that using their relative masses into how they're combining particle to particle? And this is just like going to the hardware store and saying, I want 20 pounds of paper and 5 pounds of scissors because I know the relative masses are 4 to 1, and I want 1 pair of scissors for every pair of paper. So you would get that 1-to-1 correspondence by using their relative masses. Here you don't want 1-to-1 correspondences, but if you want 4 times as much paper, take 4 relative masses and just 1 relative mass of the scissors. And I'll put the relative masses up there. I'll just go back one. I'll write the relative masses down here so you have them. So relative masses. So we know hydrogen, relative mass 1, sulfur atoms, relative mass 32, oxygen, relative mass 16, and what else is on there? Carbon, relative mass 12. So those are the relative masses. I'll write them up again. I'll start the machine, talk about this, and see what you come up with. What I was going to say is on the exam, you'll have a periodic table. We'll give you a specific one to look at. Think about that for a minute and take a vote. Okay, let's come back together here and see what you're thinking. So push your button if you haven't so far, and we'll see. We don't have many responses. Are there? Low Zoom attendance. Most of us are thinking H8OC2S, the last one in the column there. Let's go through that together. So we're saying here are mass ratios. There are the relative masses. And we can say to ourselves then, relative to 30 grams of sulfur, that's 1 mole of sulfur. You could call that 1 mole. Then half that relative mass gives you 1 mole of oxygen. Do you have half that? You do. That's great. So half the mass, you do have half the mass. Half the mass represents a mole of oxygen. So that's 1 to 1. You got 1 to 1 there. 3/4 of that mass. So you have the 3/4 mass ratio for carbon sulfur. 3/4 of that, 32 is 24 grams. So you have 24 grams of carbon, which represents 2 particles per sulfur. So you can write that down, 2 moles. And you can take hydrogen. You have 1/4 of the mass, 1/4 of 32 grams. So you have 8 grams. And that's 8 times the particles in hydrogen. So you come up with H8OC2S. So those are the those were the mass percentages. Now these are the mole percentages. You have mostly by particle, you have lots of hydrogen, even though that's not much of the mass. And the sulfur and oxygen have a small mass contribution to that molecule. Excuse me, a small particle contribution to that molecule. There's only one of those where there's 8 hydrogens. So we understand that. We also understand that this is an empirical formula. That is, it might not be the correct formula. Any multiple of those numbers would also have those same mass ratios. All the mass ratios give you is the relative numbers of the particles. That gives you a formula, but not potentially not the exact formula. To get to the exact formula, that you would have to know what's the relative mass of this exact compound. So what's the molar mass of that compound? Then you could say, I know exactly how many hydrogens, oxygens, carbons, and sulfurs are in there. Okay, so you can take your screenshots of that. I'll get out of the way. And here's something. So what is this exam that you're going to take online? I'll lower the intensity of the screen here to make that maybe a little easier to see. So what can you use on the exam? We're not going to be open book, open note. That is, you don't have the oracle of the internet at your disposal. What we'd like you to do is we're going to provide you with a exam equation sheet, and we can provide that to you this morning. I was going to do it over the weekend. I forgot. And you'll be provided with a separate sheet that has the important figures on the exam. So as you're paging through the exam, you can look back to the important figures that are there. And that's all you need to get through that. And your noggin. They're on a lot of numerical calculations. And we know first thing you'll have to answer on the exam is agree to those conditions. Say, I have academic integrity. I'm not going to look at other sources. I'm not going to talk to other people. I'm going to do this by myself with the resources you give me. So take that seriously. And one reason you should take it seriously is here. So here's last summer. So I asked this question: what's the most accurate value for the standard enthalpy of formation of ethanol that can be calculated from the data in the table given. So there's a table. This even turned out to be a homework problem. I think you guys might have done this as homework this semester. And that's true. I'm giving you typical exam questions as homework. So you've seen exam questions already. So the correct answer, 375, 37% of the people did it. This answer, 227, is the answer you get if you Google standard enthalpy of formation of ethanol. So many people Googled that and put in the answer. Okay? And where did that get them? I know that academic integrity is going to strain you. It will not pay off. Okay? Do the exam with the information given, and you'll be successful. Also B courses in the quiz mode is keeping track of what you do, how many windows are open when you click in and out of the window. So be aware that be academic integrity and, big brother. Okay, that's our lesson for the day. We talked about the mass spectrometer, the thing we want to know about the mass spectrometer. And I think you know me well enough to know that if we're going to talk about moles and relative masses and ratios and stuff, we're probably going to do it with a mass spectrum rather than, in high school, maybe you or your previous chemistry class, maybe you haven't had one yet, they probably said balance this chemical equation. I think you can do that. Those balanced numbers show up as ratios of particles. So the mass spectrometer tells you how many particles at different masses you would get. And we saw how that worked. So we saw, oopsie, one too many there. Why isn't it going backwards? Go back. There we go. We saw that you have masses, so you get masses of different particles, and the height was telling you the relative number of particles, or number of moles, if you want to do it. Those are the same. You can use those words interchangeably. Number of particles, number of moles. So the ratios were important. So here, it looks like there's, 3/4, there's 4:3, oxygen 16 to water in there, about a 4:3 ratio or a 5:4 ratio. So that tells you the particles, something about the nature of the particles, its mass. We know mass doesn't identify it, but if we know what we put in to the spectrometer, we know the masses, and we can help identify that. If we know what we think the products of the reaction are, we know what we expect to find. So mass is good, and it also tells us the relative amounts. So let me ask you this: what is the molecular formula of the molecule whose combustion reaction in excess oxygen is followed by this mass spectrum? So here I shoot, when you're doing these in the gas phase, you take a little syringe, you take out some of the reactant, and you shoot it into your mass spectrometer. And then after the reaction's done, you take a little squirt out and you squirt that into the mass spectrometer. And the reactant side gave you this, the product side gave you that. So with that kind of information, can you determine the molecular formula of the combustion reaction? Which molecule did we burn in that reaction? Think about that for a second. We'll turn on the machine. Okay, great discussion in my breakout room, famous breakout room 9. I don't know how famous it is. Let's see what you're thinking. A clear majority are thinking B, the middle one. So let's see what you're thinking. We'll go through it together. So, no explanation. Okay, we'll annotate this a little bit. I agree with the B's. So you have here in the reactants something at mass 30 and something at mass 32. Lots of something at mass 32. And we said excess oxygen. So this is representing maybe lots of oxygen and something else at mass 30. So that could be the reactant. And that would lean towards this one, which is mass 30. And carbon and oxygen, that's 12 and 16, 28, 30 here as well. And here, 12 and 16 is 28 again, and 4 more is 32. So this is 32, but you can't rule that one out yet because it's underneath. It could be there underneath this. So can't totally rule it out, but then what would this be? But remember, this is just a mass. It doesn't uniquely identify what's there. So that's oxygen, maybe some methanol. So you have to look at the products. And what do the products tell you? Well, carbon dioxide and water is formed in any combustion. And remember, I'm not going to tell you that. If you burn a hydrocarbon and oxygen, you get carbon dioxide and water. So this ratio, that's how many water molecules per carbon dioxide. So that looks like about 3 to 2. So a 3 to 2 ratio, 2 carbons in a carbon dioxide for 3 waters, that's 6 hydrogens. So 2 to 6 looks about what you got, and 2 to 6 is a possibility. And then your excess oxygen showed up as well. It wasn't all consumed. Okay, wonderful. I'm glad you guys are rocking on that. So that tells me you're prepared for this exam. So we talked about entropy, phase transitions, statistical nature, and the thermodynamic nature of entropy, and even this idea that entropies are absolute. They're compared to the absolute zero, a perfect crystal with one way to arrange things. Everything else has more ways to arrange them, more microstates. So that has greater entropy. And we talked about how free energy tracks the entropy of the universe for us. So we don't have to keep track of the entropy of the universe to determine if something is favored. 2 system variables, the enthalpy of the system and the entropy of the system, as well as what temperature it is, tells us whether the reaction is favored at equilibrium, the products are favored at equilibrium, and a negative free energy means we are favored at equilibrium. So spontaneous processes, free energy change is less than 0, and we know that corresponds to being favored at equilibrium. It doesn't mean every single reactant turns to products and the reaction goes to completion. I should put that on. That's not an exam question, but the difference between those two things is, that's actually an interesting, oh, you can see my mind think. Okay, I'm going to go through how I think about an exam question because I think that's helpful to you. So if a reaction does go to completion, but the thermodynamics, the free energy says there's the standard state free energy difference tells you the position of the equilibrium, but you can go past equilibrium. There's lots of ways to get past equilibrium. You could go kinetically past it, like combustions. They go blowing by equilibrium. Maybe you don't have a chance to get back. So there are ways to go to completion and use up all your products or all your reactants and have just products. But that isn't necessarily, that amount isn't predicted by the free energy change. All the free energy change told you is that at equilibrium, they would be favored. So a good exam question would be, do you understand the difference between those things? So I could ask, a reaction goes to completion. How does that compare to the standard state free energy difference? And you would say, well, I can, from the standard state free energy difference, I can calculate an equilibrium constant that says it doesn't go all the way to completion. So there are lots more products than there should be. So what does free energy say about that distribution of reactants and products? Well, the free energy difference of those says I should go back to get to equilibrium. So that's the kind of question I would ask you. What that thing went to completion, why? I might not ask you that, but I could say it kinetically went there, went faster, very, very fast. And right now it's down there. How does that compare to the free energy difference? Well, the free energy difference says it would go in that direction, but it said it stopped at equilibrium somewhere. Okay, cool. Next time I'll put that one on. Okay, which of the following will react with iron oxide to produce molten iron? Now, we need to know these thermodynamic parameters, and we saw free energies of formation for the elements in their standard state are defined to be 0. The enthalpies of formation of the elements in their standard state are defined to be 0. So we can take enthalpies of products minus enthalpies of reactants, free energies of products minus free energies of reactants. Those are scaling. You should be drawing these pictures. Just keep drawing these pictures. This thing is up here on enthalpy hill. This thing is down here on enthalpy hill. It's likely to go this way unless there's an entropy contribution that's very large. Free energy, if it's up here and down here, then yes, it's going to go that way. So you can rank these things and just go ahead and draw lines on your paper and put the things on the hill rather than the table. So you see what's going on. So here are some numbers. So I'm going to go to the chem quiz. I'm going to start it because when we start it, you get that screen capture. And I'll go and I'll show you this one. So these thermodynamic parameters are there. Oh, poopity poop. That is not the best table for that. I must have changed the table. Okay. The number you need. Oh, I can write the number you need. Is iron oxide here? So you need iron oxide and you need aluminum oxide. Neither of them are there. I'll just write them on the. So I'll just say that I'll give you the parameters you need. And on the exam, I do this too. I don't want you to go find a table of Fe2O. That's around minus 800 kilojoules per mole. And the standard heat of formation of aluminum oxide is around minus 1600. Okay, so those things in mind, which of these might react with iron oxide? So carbon solid, iron solid, or aluminum solid are your choices to produce molten iron. Let's think about that for a minute, and we'll take a vote. Okay. I'm back with you. I didn't join the Zoom room because my batteries died on the mic. But I'm going to bring us back together because we'll discuss this one. This is not a super intuitive one. But instructive to go through together. So first, let's see what you're thinking. I'm interested to see. So push your button if you haven't yet. Think. Aluminum, solid, overwhelming. Overwhelming. How can it be overwhelming? You've seen this before? It's on the homework and you've done the homework. Woohoo! Okay, well then I think you'll appreciate an explanation because you did the homework and maybe you'd like to see at least my explanation. My explanations are maybe not as good as your student instructors, but so why is that the case? Well, what we have here is a number I can get from a table. The number I can get is the standard enthalpy of formation of iron oxide. That is this reaction. Elements in their standard states making iron oxide. I can throw that 2 lines on the board. Now, the aluminum also an element in standard state, and solid carbon. Those would all be up here. Aluminum in standard state. If I have aluminum in standard state and oxygen, I can form aluminum oxide. And that was the 1600 number. That's the big number. So now I can see going from iron oxide to aluminum oxide is a decrease, something like 800 kilojoules per mole. The question is, how do I get there? Well, it starts to be relatively obvious that if I add aluminum, it looks like what can happen is, well, this is the thermodynamically more stable compound. So if aluminum can have those oxygen atoms and iron can be produced, then this reaction is the favored one. You would end up down here at the lowest. So iron solid, and now we can just say in general, aluminum oxide plus iron solid is the thermodynamically more stable combination compared to iron oxide and aluminum solid. Okay. One of the reasons we do this is a very exothermic reaction. And I wish you were here in Pimentel. We would do this chemical reaction for you. When we do it in Pimentel, we have to move the first 2 rows of the auditorium back out of the way and stand there with fire extinguishers. Because indeed, it's going to react exothermically enough and fast enough to form molten iron. So we'll have Lonnie do that in a controlled environment in the demo lab. So here's Lonnie. So there's that crucible, and he's got aluminum oxide and aluminum metal and iron oxide in there. He's also got a fuse made of magnesium. So we're going to zip along till I give him a chance to light the fuse. Okay, there he's lighting the magnesium fuse. Oh, for goodness sakes. Lonnie. Go and light the fuse right there. And now go from there. There's lit the fuse. Magnesium burns very brightly. And then the reaction goes crazy. You'll see, oh, that amazing explosion. And we'll play it back in slow-mo. So here's the crucible. That's the magnesium fuse burning. It starts the reaction, and we need that activation energy. Once the reaction is going, now you can see it get bright orange and the iron and aluminum. And then look at that. Molten flippin' iron comes pouring out of the bottom of the crucible. That is a pile of molten iron. That's how much reaction enthalpy is released in that. And of course, Lonnie, always thinking ahead, has a marshmallow ready to roast. Ooh, he likes them toasty. So as always, I wish you guys were here. It would be fun to be in Pimentel with you. It would be fun to see all your faces every day, of course. So definitely come by and say hi when you do get to campus if you do. Okay, the triple point of water, which is true of the sublimation. So we talked about this only briefly, and you don't have to know anything about phase diagrams except that these lines and points tell you where things are in equilibrium, the pressures and temperatures, because that's what we're interested in. It turns out there's a three-way equilibrium at the triple point. Solid, liquid, gas, all in equilibrium. It's a wacky point. You don't expect the solid and the gas. What does that mean? The universe is indifferent. The entropy of the universe does not change, 0, to go from solid water to gaseous water under those conditions. Universe is indifferent. You can be the solid, or you can be the gas, or the liquid, or the solid, or the gas. At the triple point, there's equilibrium between those. There's no free energy penalty to switch between them. That's the special case where entropy of the universe is 0. So, which is true about that case? Free energy of that reaction, and you can see there's very low pressure, very low temperature. The free energy is bigger than 0, equal to 0, less than 0. Let's talk through this one, and we'll do the next one. So it's at equilibrium. The free energy difference, and now this is not standard state. There's no degree sign there. That means the free energy difference between the products the way they are right now and the reactants the way they are right now, not at 1 atmosphere and 1 molar and all those things. Where they are right now, what's the free energy difference between them? And if they're at equilibrium, the free energy difference between them is 0. That indicates entropy. Entropy of the universe is the same on either side, also 0. Okay? So equilibrium, we've already decided equilibrium means entropy of the universe is 0, which means free energy measured right there is 0, not standard state free energy. Okay? I think that's going to be the next one. That's why I say that. Yes. So at the triple point of water, now you need to think, if I am talking about the standard state of sublimation now, solid going to gas, under standard conditions, what's the difference between those two? And again, you can do standard conditions at different temperatures. The important thing about standard conditions is 1 molar and 1 atmosphere and pure solids and liquids are present. Okay. Talk about that. Let's take a vote. I will start the counter. Okay, let's come back together and see what you're thinking. You are thinking A, the standard state free energy. It's not unanimous. It's not even a majority, but a lot of us are thinking A. And that is the case. I'm harping on this, and do I feel bad about harping on it? I don't know. The standard state, it's this simple thing, and I don't know why it's kind of pulling teeth. If I say standard state, that means it's just this artificial thing where you make every product and reactant 1 atmosphere, everything, and or 1 molar if they're in solution, or they're pure liquids and solids. That's just a made up place, but you can make that place anywhere. If you make it under the conditions of the triple point of water, then you're saying, well, I have to go here, but I'm going to be 1 atmosphere of pressure instead of that 0.006 atmospheres of pressure. So then it kind of just turns into Le Chatelier's problem. If I'm here at 1 atmosphere of pressure, I know the equilibrium state. You just told me it was 0.006. So that has to decrease. That's a product. It has to be decreased. Q is greater than K. It's going to go towards reactants. And what does going towards reactants mean? Going towards reactants means delta G is positive. They want to stay the favored form. The equilibrium favors reactants is what delta G positive means. Delta G negative, it favors products. And we knew that was the case. There was just a tiny partial pressure of water. It was favoring the reactants when I write it H2O solid going to H2O gas. That's what the standard state tells you. If you know the standard state, if you know this number, you can calculate that K, right? Delta G standard equals minus RT ln K. Think about that. The position of the equilibrium and the standard state free energy are linked. That's what the take-home lesson is. Okay, we're going to kill this. Triple point of water. Ice, liquid, and vapor are all in equilibrium, which is true of the liquid to solid transition for the system entropy. We'll talk about this now together. So the liquid, oops, did I not do the answer? Yes. The liquid to solid, that's what I asked about, right? Sorry, going too fast. Ding, ding, ding. Okay, you guys can take your screenshot there if you want. Yes, liquid to solid transition. And the system. Well, if it's liquid to solid, the system is changing liquid to solid. So that's easy, right? If it's changing liquid to solid, that's a decrease in the number of microstates. Decrease in the number of ways you can do that. Okay, delta S is negative. That's supposed to be easy. Sometimes you, we get talking, and I say that I really honestly am trying to give you an easy question, but it's coming at you so fast, and there's so much to digest. You can't see through all the cloud of war to see that that's easy. Okay, so relax on the exam. I don't ask trick questions on the exam. I ask these kind of questions that I think are easy. They are the basics, is what I want you to know. So that system entropy 0. What does this mean about, well, wait, you said it's at equilibrium. Why isn't delta S 0? It's delta S of the universe that's 0 if they're at equilibrium. That means if the universe does not care, it's in equilibrium. The universe does not care whether you are the gas or liquid, or in this case, solid or liquid, under those very specific conditions, because those very specific conditions says, oh, wow, the microstates actually are going to be similar. Or when I go from one to the other, the entropy of the universe, the surroundings take a hit. So if in this case it went, entropy of the system is, in that case, negative, well, the entropy of the surroundings positive, so that entropy of the universe is the same on both sides. So I say it doesn't matter which state you are in. Still entropy there, It's just the same on both sides, but it's hard. It's tricky to get to those conditions. So you're going to guess, okay, so here I've already told you the answer to this. So we are at equilibrium. So if we are at equilibrium, entropy of the universe is 0 in this case. So that's what the equilibrium condition is. Delta G equals delta H minus T delta S. And that is, this delta G thing is related to the entropy of the universe. This actually has to be less than delta S of the universe. Less than because of that minus sign. Okay? So when delta G is 0, we are at equilibrium. The entropy of the universe is at equilibrium. And you get some information there. That tells you delta H is equal to T delta S. That's why you're in equilibrium. The enthalpic part is beautifully balanced by the entropic part. Okay, there's the table you needed. That had iron oxide and aluminum oxide in it. Bunch of review. Okay, which has the lowest relative enthalpy of formation? We have two reactions. This is the famous one we were talking about, the Haber process, nitrogen and hydrogen forming ammonia. And this is nitrogen and oxygen forming N2O. So this kind of involving pollution. These things are catalyzed by other pollutants and ultraviolet rays in the atmosphere. So which of those has the lowest relative enthalpy of formation? And we're not going to a table. We're just looking at what's there. So I'll start the machine. Let's talk about that. Okay, so let's see what you're thinking about that one. And a couple more people could push a button. There's not too many of you. Let's get a little bit more. If you haven't yet, just take a stab. Of course, you're never judged on this. Many of us are thinking C, the vast majority C, and I'm glad you're thinking C. I had Alice, who's sitting in China, brilliantly explain this to the group. Exactly, almost. She was like taking the words out of my mouth. That's what I would have said. So these are the reactions that represent the enthalpy of formation of those two things. Why? These are elements in their standard state. So you could prepare those all at 1 atmosphere. If you prepared those at 1 atmosphere too, it would still be exothermic. The energy difference between those all in their standard state. NH3 is lower. So compared to the elements in their standard state, which is the 0, ammonia, you go downhill. That's low in enthalpy. Draw that line there. You go uphill, endothermic, to get there. Okay? So if I'm looking at relative enthalpies of formation, which is lower? NH3 is lower, and in between are the elements in their standard states for this one. Okay? So if you understood that, you understood I don't need to know the numbers in that case. And you know I love this stuff. That's what I'm going to ask you on the exam, because you can't go to Google and look up a number. You to understand this, you have to say, oh, I understand what exothermic and endothermic is. I have to be able to rank them. I can do it quickly from this data if I understand. Excellent. So for which are the products favored at high temperature? Oh, brilliant. Okay, I'll stop this. Stop that and start a new one. Well, if you can do this, we're running short of time, but if you can do this, yes, you are ready. You've done very well in your preparation for this. Ooh, I love this one. And again, all you need to know is what's here. You don't need to know one single number to do this. Soak it in. Ready? I'll go talk to somebody. intimidating or something or scary? I'm both those things. Oh, my mic was on. Sorry. I was musing to myself coming back from the Zoom room. I only had one person talk. One person said hi in the chat, and one person said a few words. We had a nice conversation. But turn on your mic, say hi. Turn on your cameras. I want to see your faces. You don't have to turn on cameras. I know it's you don't have to get dressed or out of bed for this. But say hi. I'm not gonna bite anybody's head off. I want to talk to you. Okay, so how do we know this? This, like I said, is incorporating everything, really, virtually everything we want to know about thermodynamics. So beautiful in one question. Okay, you don't need any numbers. You say to yourself, what determines whether things are favored, period, at equilibrium? What tells you things are favored at equilibrium? The standard state free energy difference tells you that. If the standard state free energy difference is negative, then the products are favored at equilibrium. So this one, you say to yourself, I can plot the free energy difference versus temperature. It's a straight line. I don't know if I put the numbers here, but is this one where I changed it and I forgot to do the thingamabobber again? Let's go through this without that answer. Do I go through the math? No. Shoot. I think I grabbed the wrong solution again. I'm sorry. So you can plot. Oh. Well, let's go through it. Yeah, let's just go through this. A little messed up maybe here on the figures. Let's go through it and figure it out. So I told you which was endothermic and which was exothermic. So this one is endothermic. Sorry. That one is exothermic. So delta. Go to the pen, please. Go back one more. So that is not there. Go to the pen. Okay. So we said this one exothermic, and we said this one endothermic. Okay, and we already had those kind of sketched out. So you could make this one from this one. This one's overall favored in that case. So the plot that we want to write is the free energy is the enthalpy difference between the products and reactants in their standard states versus the entropy difference between the products and their standard states. And it's a function of temperature. So what we say is, well, H is the intercept. This is a y equals mx plus b situation, the formula of a straight line. B is the y-intercept. So they're going to be different. For this one, it's exothermic. Y-intercept negative. For this one, endothermic. Y-intercept positive. The slope is determined by the sign of delta S. For this one, we have, in both cases, fewer particles on the reactant side. So in both those cases, the entropy decreases. Delta S is negative for both of those. So delta S, negative, call that less than 0. T is always positive, so it's minus delta S. Minus a minus is positive, so the slopes are both positive. And what was the question? Which becomes more spontaneous, or for which are the reactions favored at high temperatures? Is that the question? For which are the products favored at high temperatures? So what's favored at high temperatures? Delta G, the standard state free energy difference, becomes positive at high temperatures. So these guys, you have a case where neither is the answer. You get to high temperatures and the reactants are favored the higher the temperature goes. If you go to low temperature, at least this one, products are favored. But going to high temperatures, this one is in that horrible case where it's never favored. Delta G is always positive, regardless of what temperature you go to. Okay? Wonderful. Sorry, I did that thing where I did bad editing on the slides. It's getting close to time. I want to do this, and I'll tell you why I want to do it. There's something really similar on the exam. So, shouldn't have said that out loud. Is everyone listening? Let's do this one. I'll talk through it because we're running short on time. But and these are the ones I love where you just rank things and tell me what's going on. Okay? Which releases the greatest amount of energy? First and foremost, these are all combustion reactions. They all release energy. They're all exothermic. They all make carbon dioxide and water. Okay? They all react with oxygen. In this case, the same amount of oxygen. Throw that out. We don't care about that. That's the same in everything. It's not going to affect any differences. I have the reactions balanced. So the question is, it's all ethene here, but the question is whether it's a gas or liquid, and whether you make gas or liquid water in the products. So how do you go through that? Well, you know the reactant side, product side, overall, the reactants are higher in energy than the products. The products are carbon dioxide and water. In this case, carbon dioxide is the same for all of them too. So I'll just use that as our symbol. Carbon dioxide and water are produced, but in every case, it's gaseous carbon dioxide. So that doesn't really matter. So every case this is true. What matters is, well, you can kind of tweak where these guys start. So what's the relationship between gas and liquid? Where should I put on this overall diagram C2H2 liquid? Well, I should put it slightly lower. Why is that? Because I know to get from the liquid to the gas, I'd have to put in energy. So it has to be lower. How much lower? We don't know yet. In the final, you're going to be able to tell me, but not now. This one, same thing. I have to put gaseous water. Gaseous water. And here I've made the gap much bigger. We've talked about that already. Water has this unusually high enthalpy of vaporization. By the final, you will be able to put the relative sizes, not the exact numbers, but you'll be able to put those relative sizes on there, because we'll talk. What causes those relative sizes? This is it on the exam. What causes those relative sizes? I'm just not going to ask you about it specifically. What causes the relative sizes is the potential energies, and kinetic energies are the total energies you can have. This one must have more potential energy in the liquid state than this has in the liquid state. Those potential energies are the attractions between the molecules. This has more attractions between the molecules than that one. You have to put more energy in before it turns into kinetic energy, and it is in the gas phase. And then once you're in the gas phase, we're saying that's all kinetic energy, no potential energy. Okay? But that's it. That's the whole story. Now I can write them all down. Those are the two enthalpies of vaporization. You should be able to write that down. If I drew this line on the exam, and you know you've done the homework, sometimes I just draw a line and ask you to identify it. That's the enthalpy of vaporization of water. Okay? That's the A situation, going from gas to liquid. The B situation is gas to gas. And the C situation is liquid to liquid. And there you go, graphically thrown out there, no calculations, all stuff that you know. It's a great final exam question because you'd also have to predict these sizes. Turns out it almost doesn't matter what those sizes are. They'd have to be dramatically different to change the answer. But those sizes, those relative sizes, allow you to rank B and C relative to each other. Because B and C matter, what matters there is the enthalpy of vaporization of water greater than the enthalpy of vaporization of the ethene? And it is in this case. So that gap is bigger than that gap. And that means C is bigger than B. So if you did have to, I didn't ask you which was, if I asked you which was the greatest and order them, you could still order them. You would say C. It's bigger than B. Okay? All right, guys. That was super productive. Every single thing I said, basically, you'll see on the exam. So you've got, what, 8 hours or so? Get yourself ready. I think there's might be office hours and stuff coming up. I don't know. But ask questions. See you tomorrow. Oh, I have something important to say. I'll put this as an announcement. The day after the exam, we put the most missed exam question up as a chem quiz. And if you get it right, the morning after, we give you that point back on the exam. Okay, so you'll see that first thing tomorrow. Good luck tonight. Signing off from Berkeley.